All right, sorry for being a minute late, or a couple minutes late. So here's what we're going to do today. We're going to start talking about this completely different type of data structure, which many of you have actually probably heard about in some form or another. But it's called, well, the function is called hashing that we'll be talking about. And we'll eventually get into talking about these things called hash tables. Okay, completely different type of data structure, but actually a really important one, as it turns out, for CS and for programming in general. Hoping the slides here come out. They're a slightly different format than last time, but hopefully you should be able to read that. OK, here's the actual schedule. So we're going to talk about a Unix tip of the day. On Monday, I mentioned these things called regular expressions. I'm just going to show you a little bit more about regular expressions, because you'll probably see those at some point again in your CS career, and you might as well start to kind of understand what they are. Then I'll make some comments on homework 4 and homework 3 grades. If you didn't get an email about your homework 3 grade, it meant either that it didn't get graded because it didn't end up in provide for some reason, or the email system just kind of lost it. A couple people didn't get emails last time, I know. So if you didn't get an email about homework 3, email me and I will send it back. And I'll talk a little bit more about that. OK, and then we'll talk about hashing. And this idea of hashing. And you'll notice I put some numbers around the room that will become apparent as we get into the hashing lesson. Questions before we go? All right. Oh, quick comment on TAs in Halligan. Last night, I guess there was some concern about the fact there probably should have been TAs. As it turns out, I don't believe there should have actually been TAs in Halligan after like 9 p.m. last night. Over the next week, we'll have more TAs in there. The schedule, if you look at the schedule online, it says something about like alternate or additional TAs or something. I think that hadn't kicked in yet, and it probably should have. But we'll make sure there's TAs going forward when most of you guys are going to be there. I'm going to try to do the best we can on that. OK? All right, regular expressions. So I mentioned this the other day. Regular expressions are, it's actually a sequence of characters that can be used to search for words and other sequences of characters inside some text. OK? And we generally use it for pattern matching. Like if you have a bunch of text and you want to find out where the various parts of some pattern are that you have, whether it's a word or a character or a set of characters or something like that, you can use regular expressions. OK? The most basic regular expression is a simple letter. Like if you have a regular expression A without the little quotes around it, that matches the first A in some expression that you've got, right? In fact, in some cases, it matches all of them, depending on what you're actually using. But in this case, A matches the first A in the apple was eaten. OK? There are other A's in there. Depending on the regular expression function you're using for whatever language you happen to be programming, it may make a difference. But what you can do is, yeah, this one actually does both. This is a little hard to see. Hold on. See if I can get it. There we go. OK, so that you can go online to this regexpal.com and actually test these things out. This one happens to match all of the A's in this expression here. So A matches A there, and A there. And that's a regular expression. It's just a what matching. No great amazingness about that, right? OK, so that's the first one. Then you can get into matching things like multiple letters. So if you wanted to match E and A, or I should say E or A in the string, you would put it in little brackets like this, and you say EA, and it would match this whole, the E there, and the A there, and the E there, et cetera. Kind of cool. You can also match ranges. A through M matches any of the letters that are between A, well, inclusive between A and M. All right. Then you can match wildcards as well. Now, here's the thing about regular expressions. They are like super duper powerful. OK, and it has to do with the ability to match wildcards and ranges and lots of different functions. So you can use them for a lot of different things. You can't use them for everything, but you can use them for a lot of different things. And this is one right here. If you have a period, right, well, period matches any character. So if I say A period period, that will match any time it sees A and then two characters after it in line. So that's actually A, S, and then the space also matches. And then here it's ATE, right? A period period matches those. Kind of neat. You can match with a star, but this is a little different than you might have thought of in some other matching algorithms. Star says for the previous character, however many matches that character is in a row, it will match, 0 or more. So the character P star will match however many P's there are, right, after the P. So it's got to have at least one there, and then however many 0 or more matches. So that matches P, and it also matches P. You can kind of start to see how powerful this can be once you dig into it a little bit. A dot star would say A and then any number of any other characters after that. So that would be A period star, any number of characters after period, so that's everything else, actually. You can, and by the way, this regular expression tester, let's see, A period star. So the apple is in A period star says everything after apple, or everything after A, rather. Just A period will be the A and then any one letter. A period would be 2, etc. Okay, or 3 rather. Kind of get the idea? All right. Then you can also match things at you can have these anchor characters, which will match things at the beginning or at the end of a string. So if you have a character or the caret there and then it will match everything. Actually, it should just match the there. I think it would probably just match the That's probably incorrect. Let's see. Yeah, there we go. It just does the first one, but it means it has to be at the beginning, right? If you said beginning apple, no, that's not going to match because apple's not at the beginning of your string. Kind of neat. Okay. And there's one at the end as well. And so you can start to look at some of these and say, OK, look at this one. D period star, or $. That means anything where it's D period and then at the end. Now, by the way, period means any character. So the fact there's a period in there, you have to do something special about that. Right? So D period and then the end means it will match D at the end, D period when it comes at the end, or actually D anything when it comes at the end. Okay. If you want to match a character that's a special character, like you wanted to actually match the period, you put a little backslash. A lot of times we use backslash for special characters, right? So if you had the apple was poisoned, darn, right, and you had poisoned / period, well, that would pick this up, right, because of the fact that it was. Oh, I didn't have a change there. I must have not had a period here. Well, this looks like this. Oh, here we go. This one matches poison / period will not match this one because there is no actual period there. That's what it is. And then finally, the apple was poisoned yesterday. Same thing. This one will match it because that period means wildcard. So you just have to think about all these things when you do it. As I said, there's lots of regular expression testers online. You can kind of throw some strings in there and practice it if you want. And you use them in Linux, specifically in grep and sed, which we've already talked about a couple times. And you'll use it in lots of different scripting languages. If you do any JavaScript, you'll probably use regular expressions at some point. Perl uses regular expressions. Python can use regular expressions, but actually it's not quite as popular. C++, there is a regular expression like module you can, or a class, but not used too often. Okay? Questions on regular expressions? Pretty powerful. Like when you get in, there's like whole books written on regular expressions, believe it or not. Questions? OK. All right. Let's go into, well, actually, before I was going to go into hashing, we'll talk about the homework. Homework 3, as I said, you should have gotten your grades. Grades were pretty good on that. Please email me if you didn't get them back. Homework 4. There have been a whole number of very good questions on Piazza about various kind of big ideas about how we're analyzing our sorting algorithms, what kinds of sorts we can use, how to apply them. So I mean, I think that's good. I mean, I like to see that kind of level of discourse on Piazza. So keep the questions coming if you have specific questions about your designs or what have you. The design choices, completely up to you. Like if you haven't really started the assignment yet, you get to make the choices. I mean, I do make you do one specific sort, but the other two are more or less up to you. You have to do one out of a list, but you get to do lots of choices. So this is as broad as you want on that. The readme.txt, very important this time. Why? Because you have to explain what your algorithms are doing. Like you have to talk about the asymptotic complexity, you have to talk about the algorithm itself, you have to talk about some of the choices you made. So we're gonna grade that more heavily than some of the other README files before. Okay, just make sure that you've got detail in there that says it doesn't have to be pages and pages, but it should at least give the description of the algorithm, some of the choices you might have made to do that. I ended up using a linked list instead of an array because I thought it would be faster for blah blah blah, whatever. Okay, and then describe the actual complexity. You do not have to go and figure out the average complexity. Right? You can look that up. If you're building a sort that has been done before, somebody has probably already figured out the average complexity. You should be able to figure out the worst case and best case just by doing some analysis yourself. If you can't, that's fine too. Some of these are hard, so I get that. But you can do that. So anybody have any questions at this point on the homework, on homework 4, or comments on it? No? Yes, Kuyan.
So we change the name of the sort 2 and sort 3 to the name of our own sort?
No, leave them as sort 2 and sort 3, because otherwise they won't get provided correctly. Leave them as sort 2 and sort 3, and just in the header or in the comments of those say what sort it is, and then the README as well. Yeah.
Can you explain the if, def, and if at the beginning of the?
Oh, sure. Well, OK, the question is about you'll notice there's a pound define if def, pound if def, and end if, and so forth. OK, this is a little bit advanced, but basically what happens is when you read in a header file, you don't want to redefine things that might have been read in already, because then it would, like, the compiler can't figure it out. So what you do is you put basically check cases at the top and the bottom. At the top basically it says, if this header's already been read before, don't read it again, because you've already got the information. That's all it is. Just saying don't reread it. So it means you can include the same header in multiple files, and the compiler won't complain about it. That's all that's for. Okay. Other questions on homework, comments? Hope it's going all right. The questions I've had by individual students have been great. So keep it up. And it's due on Sunday night, I believe. Nothing else? All right. OK, so we are going to start out talking about this other topic called hashing. Let me just set up just kind of a little brainstorm for you here. Let's say you have some 2-letter words, like ox, right? A 2-letter word. And you have its associated definition. Like you've got a dictionary, and it's got words in it. And you've got an associated definition. And you want to store the value of that definition based on looking up the word itself. Right? So you look up ox, and hopefully your program will be able to return a bovine trained as a draft animal, right? Or whatever the definition of ox is, depending on your dictionary. Okay? That's the kind of thing that we're trying to do already. Now, we have already talked about keys and values. We generally haven't talked about keys that aren't numbers, like the fact that the key is ox. Well, we have talked about a little bit about words in general and comparing words. But what we're going to do here is actually a whole different idea of how we're going to get ox to what we call map to bovine. In other words, we're going to have that key itself and do something with it, and then produce an output that's bovine, okay, or the definition. So that's what we're trying to set up here. Okay. We've discussed other ways to store these types of information. Obviously, this whole class is about this stuff, right? We've got lists, which can be arrays or linked lists. We've got, or containers, like you call them. We've got stacks and queues. We've got trees. We've got heaps and tries and so forth. And we've done some of this storing of things, right? But they all come with some trade-offs that we don't really like, right? They come with trade-offs that either involve order n behavior or order log n behavior, which is better and not terrible generally. But we want better than order n and order log n. Okay, remember that order 1 is really the one we're like always looking to get, right? Constant time for functions. And the 3 functions that we care about in this case are being able to insert into some structure, being able to find in that structure, like find the element, and then be able to remove from that structure. Okay, so we have those things. Now, some of these may not have those trade-offs as far as being order n or log n, like stacks and queues. Their operations are, in general, order 1, right? But the problem is, what can't you do with a stack or a queue of these three functions? Can't do find, right? There is no find defined on a stack or a queue. You either get with a stack, you get the topmost, right? With a queue, you get the front, right? Some queues, you might be able to get the back if you want, but that's it, right? You can't search through the actual stack and queue, okay? So we're trying to come up with something a little bit better than that. That's the basic idea, okay? Well, if we're going to try to get this order 1 complexity out of this, okay, we can do this other method that I already talked about called hashing. And as you perform this thing called hashing, which I'll define, you actually use this thing called a hash function. And what I mean by function is literally a mathematical function that you apply to your key in some fashion or another, which means that your key has to, in some sense, end up as numbers, right? But strings, each individual character has an associated number with it, right? And so you can break various keys if they're strings or even objects, right? If you've got objects, you can associate individual parts of that object in a numerical sense. So any properties or any private variables you have, if you want to use those as your input to this hashing function, you can, okay, because it's all based on our numbers. So we're going to have this cool function that we're going to actually define that will allow us to do this hashing, okay? When we return the values from a hash function, we call them a couple different things. We can call them hash values, or we can call them hash codes. You'll see that sometimes. Or sometimes we just call them hashes. Okay, so apply a function, get a hash. And that hash is what we're going to use to do this amazing complexity reduction. Okay, you'll see. All right. So here's one possible definition for a hash function. All right. Any algorithm, mathematical algorithm, that maps data to a number and that is deterministic. In other words, you have a function and you take some input number and you apply that function on it. Every single time, the answer has to be the same for that data. Okay? And we'll get into more details about why that's actually important in a little bit too. But the key here is if you do an operation on some piece of data, you need to get the same answer every single time. Okay? And if you don't, this whole system breaks down, as it turns out. What we can do, for instance, for our ox example, you can take it and you can treat each character as a base 26 character, kind of like what we've been doing in for the try, right? Where each character is associated with a number, okay? And then because it's OX, right, or OX, I guess for you guys, because it's OX, you can treat it as if it's a base 26 number in this case, right? To get the hash, and our hash function is just going to be this idea of, a base 26 representation of OX. To get the hash, what you do is, for the first letter, you do 26 times whatever the O is, which happens to be 14 in this case, plus 1 times 23. So it's like 26 to the 1 power times 14, plus 26 to the 0 power, which is 1, times 23. Okay, does that make sense how we're going to do this? It's for any letter, you can come up with the hash for it using that function. Okay, just applying this function to the actual string. For at, if you had that as your letter, what would it be? It would be A is 0, so 26 times 0, plus T is 19, so it's 1 times 19. Questions on how we apply that hash into there? Okay. Once we have that information, okay, we've now made a deterministic. Now, you believe that it's deterministic, I hope, right? Anytime you have ox, it's always going to be 387. Anytime you have at, it's always going to be 19. Deterministic. Okay, no changes there. Yeah?
There's the string that determines the number, not a number determines the string.
The string determines the number. In this case, yes. Yeah, the function you apply on the string, and then you get this number out. And the number happens to be, for ox, it happens to be 387. For at, it happens to be 19. Make sense? Good. Yeah, Eliza.
Would you be able to get the same number with a different string?
Good question. For this example, the question is, would you be able to get a different answer for the same, like a same answer for a different string? For this function, it can't be, right? Why? Because you've got independent. It's kind of like saying, if you have 1, 2, 3, 4, 5, can that also be equal to 4, 5, 6, 7, 8? Like two numbers can't have the same number, like can't be represented in the same number of things. It's the same idea with this one because you've got 26 letters, and you've got and you're doing for each letter you're doing this combination. So you can't in this case, but keep that in mind because you may be able to in a little bit. Okay, go ahead, Mark. And then.
If you're only using O to get the hash, wouldn't all octopus also have that 387?
Very good. Yeah, would octopus also have 387? Only for this, we're only using two character words right now. Yeah. So anything that was like oxen, if you only took the top two, yes, they would both do it. And that is a very good point, and actually part of kind of the meat of how we deal with these things. But for now, 2 letters at a time. That's it for our words. Okay, we're doing like kindergarten words. Not even. Yes. Zoe.
Can you explain again why you multiply 23 by 1, but why you are multiplying 14 by 26?
Sure. OK, so think of it this way. Let's say I had the number 445, right? Well, 4 is 4 times 10 plus, or 45 is 4 times 10 plus 5 times 1. All it is the base you're dealing with. So in this case, it's going to be 14 is the character position times 26 raised to the first power, just like doing a number. OK, just like doing a number. Good. Anything else on this? Yeah, Kuyan?
So 1 is 26 to the power 0.
26 to the power 0 is 1. Just like anything to the power 0 is 1. Right?
So if there's a 3-character word.
Yeah, we're not worried about 3-character words yet. We'll get there in a little bit. But you're all bringing up very good points on this stuff. Right? OK? All right, good. Henry, OK, you got a question on that?
Still don't understand why we multiply by 1.
Why you're multiplying by 1 here? OK, let me do this. Let me put the projector up a little bit here. OK, hang on. All right, I mean, I'm spending the time on this because this is kind of a key idea of this example here. OK, if I want to do 45, right? In base 10, there are 10 different characters, 0 through 9. And this one is going to be 10 to the 1 times 4 plus 10 to the 0 times 5. 10 to the 0 times 5. Right? And 10 to the 1 is 10, and 10 to the 0 is 1. Same exact thing for 26 instead of because we've got 26 characters. And I mention it as if we're base 26. All right, I mean, just because we have 26 characters, that's why it's 26. OK. So far, so good? All right. So we've got that idea down. Why does this actually help us gain this order 1 access? Well, here's what we're going to do with it. OK? We are going to take that idea that we can hash these 2-letter characters into an array, as it turns out. Okay? And when we did the definition of ox, we got 387. And if we have an array that goes up to 26 times 26, did I already have that on here? No, I didn't have the 20. Whatever 26 times 26 is, 500 and something, right? We can put ox right here. We can put maybe a string in there that says ox, or what we would really do is we would put the definition there. We would put like a string that's the definition of ox, a bovine, blah, 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 right? And that's at 387. And we could put the definition of at 19, which is what we found before. Okay? We all know that arrays have like order 1 access, right? So if you are sometime in the future looking up ox, apply the hash function, get the number 387, look in spot 387, and ta-da, you've got your definition. Okay? Insert took the same amount of time because you know where to put it in the array, right? Remove, same exact thing. For remove, it's easy. You go to 387 and like make it a null pointer again or something like that, right? Or make it an empty string or whatever, however you've defined that. Okay, and find was the same way, order 1 access. Ha-ha, we have reached it, right? This is a perfect system. Maybe not. Okay, it's almost perfect, right? But we'll see why in a second. You guys kind of already hit on the ideas here. Okay, so we take the take the hash as a key, put the value into the array, find the value, and delete it all in order 1. And if your hash value is fast, which it will be for something as simple as that, right? I mean, finding the, like doing 26 to the, well, depending on how long your word is, raising a number to a power is kind of slow. But in general, that kind of hash function is very fast, especially if we don't have really long words. 2-letter words, it's easy. It's always 26 and 1 to do the hash function. All right. So let's go back to our original idea here. We've now kind of said, we've got this thing called a hash. It's got a hash function, and we can put things into this array. OK. And we know what keys and values are. And now we've got this efficient data structure. So let's try to build this a little bit and flesh this out a little bit more. There it is, 676 words. OK. We've talked about how to do this. OK. We're going to create some function called hash code. OK. We're going to create some function called hash code, which applies that function we just talked about, 26 times the first character's number plus 1 times the second character's number, or just plus. You don't need to multiply by 1 in that case. OK. And we're going to then index that into the array. We can call the array buckets if we want. We're going to say, hey, here's all our different buckets, and we're going to put it in there, and it's great. Here's the program. Anybody recognize that? Or recognize that, that programming language? Hey, it's Scheme. Yeah, I will not make you guys know this in Scheme, right? But for those who did do Comp 50, this is what you guys did for like a whole semester, right? We'll talk about the C++ version, right? You could rewrite this in any language, obviously, but I did want to at least get, you guys, if you want to look at the Scheme one, you can. Here's what it is. It's pretty simple. OK, we're just defining our letters to be 26, or our alphabet count, or whatever. And then the words are letters times letters, which is how the total space we're going to have. In this case, 26 times 26, which is 676 or whatever, right? And then we're going to have a word in here, which is our string, which we're going to hash. OK? And then we're going to return from this hash code the actual hash function that we had. And notice this is exactly what we just talked about. It's going to be 26 in this case times the first character. And you guys know how to do this now from lab the other day, right? Word bracket 0 gives you the first character, right? Actually, did I do this one upside backwards? I think I did. I think I did this one backwards from what I just said. It would be ox being backwards, but it doesn't actually matter in this case. It's still going to be deterministic. Let's put it that way. And then we just have the word. And then we have this thing called a word dictionary. This whole idea, you can call this a number of different things. Python happens to call it a dictionary. Some other languages call it maps. Some other languages call it associative arrays. Whatever you want. We're going to call it a dictionary, because we're kind of thinking it in terms of a dictionary. OK? And in this dictionary, we define a table, which is just an array of the number of words we have. Right? And we said in this case it's going to be 676. And we are going to insert those words into the string or into the dictionary as follows. We're going to let's see, we're going to, I might have left some, oh no, here it is. The string is the def table, right? And then we're going to take in that table, we're going to set the appropriate word location to be the hash code that we want. So in other words, whatever the hash code is, we stick it in the array at the right place. End of story. Okay? I didn't do replace, or I don't think I did the remove in this one. But in terms of find, it's also very straightforward. No looping necessary. Right? We just return the position at the hash code. We hash the number, we look at the code, we look in that array location, and we return it. Okay? Questions on that so far? Yes?
Is there any difference, I guess, either speed or memory usage in making, instead of one really long array, it could be array where, say, like the row is the first character and the column?
OK, good question. Would it make a difference if it was a two-dimensional array where the row is the first character and the column was the second character or whatever? To a first approximation, it wouldn't really matter. To a second approximation, it probably would, because it's easier to read characters along this, or it's easier to read along one direction than both. But no, not really. I mean, if you wanted to do it that way, a 2D array, it'd be fine. Okay. The problem is going to be when we make longer words, Because then 3-dimensional arrays and 4-dimensional arrays gets really hairy in that case. But yeah, good question. OK. Any other questions on all what we're doing here? We're taking the number, we're taking the string, doing a hash function, placing it in our array in the right place, and then accessing it to find it, and order one, which is exactly what we want. Okay. All right. So what if we wanted to store all of our English words? There's a word. You look it up in, I think it's Wikipedia or whatever, right? There's a word that has 189,819 characters. Now, that's disputed, but it's a chemical name. So you guys who take chemistry, this is one of the reasons I was not a big fan of chemistry when I took it, was that like the chemical names, they get bigger and bigger and bigger. And there's a formula to create chemical names, right, based on other types of things. Well, there's a chemical formula which has 189,000 letters. All right, that's kind of long. The longest published word that's not debated or whatever, right, is this other word. It starts with methionoglutaminolarge. I don't even know how to pronounce that, right? And it ends with serine, right? And that's 1,900 letters long, OK? And then there's some other words. The longest word coined by a major author, right? 183 letters. I don't even know. I have no idea what it means, right? Longest word in a major dictionary, like you go to a regular dictionary and you'll find a word that's 45. Pneumano, I don't even know how to pronounce it. Anyway, 45 letters long, et cetera, right? Supercalifragilisticexpialidocious, 34, et cetera. Okay? And we can go down Shakespeare, longest word. He used a word that's 27 letters long. Okay, if we want to do our little method here, okay, and oh, by the way, anybody ever been to New Zealand? Yeah, you've been to New Zealand? There's a place in New Zealand that's called this word right here, Tamatawara, whatever. I actually spent, when I lived in Australia, I took a trip to New Zealand, and I went and found this place. It was in like the Let's Go guide. It's like, go to the longest place name on Earth. Right? I'm like, oh, cool, I want to do that. So I had a drive way out in the middle, saw the most amazing full rainbow I've ever seen in my life. It was like, I mean, it was exactly out of like a movie you'd expect from New Zealand, right? Like just open plains and like open fields and giant rainbow. Anyway, I got here and then took a picture of this sign and then drove an hour and a half back to where I was staying. Kind of, you know, it wasn't that interesting. But anyway, what this actually means, if you translate it to English, it means the summit where Tamatea, the man with the big knees, the climber of mountains, the land swallower who traveled about, played his nose flute to his loved one. Now, I mean, there's a lot of problems with that, to tell you the truth. I mean, I think, you know, first of all, what does it mean to have big knees? I don't even know what that means. But then, you know, nose flute, I don't want to go there. But so anyway, there are lots of words that we could try to put into this dictionary that are not, that don't fit in that 2-character thing, right? Well, how would we do that? When we had 2 characters, it was easy. 26 to the first power times first character plus 26 to the 0th power for the second character. If we wanted to put supercalifragilisticexpialidocious in there, we would need an array with 26 to the 34 buckets. And that's only for lowercase letters, no numbers, no any other special characters. Why? Because you'd need to, if we want to do it the way we've done it, we want every number to individually fit in its, or every word to individually get its own bucket, right? You are not going to create a 26 to the 34 length array. Not going to happen. Okay? It's too big. Okay, I don't even know how big that is in terms of like decimal numbers. 26 to the, what did I say? 34. 1.3 times 10 to the 48th. If we use BC, was that what we said we were going to use before, right? 26 to the 34th. Uh-oh, what did I do wrong? Oh, I did it wrong. 26 to the 34th. There we go. That's how long it is. You're not going to carry it. You're not going to have an array that big, right? And that's just to store the supercalifragilisticexpialidocious and all the other words that are that long or fewer. Okay? Can't do it. And by the way, you wouldn't want to do it. I mean, not even if you did have that amount of space. Think about how sparse that would be. Think about all the words that aren't, all the positions for words that are like zy, 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 l, zy, zy, you know, all that, right? I mean, all those ones would be completely empty. And you'd get, every so often, you'd get a word popping up, right? But otherwise, it would be a very, very sparse and terrible data structure. And besides the fact, English only has like 700,000 words in it, right? So hopefully we'll be able to get a data structure that if we wanted to store all of our English words, it's only 700,000 long, only being a relative term, but still not 26 to the 34th. OK, so we have a slight problem here. OK, we have a slight problem with our methodology of doing this. Yes, we get order 1 access. No, we can't actually legitimately do this for anything that's not trivial. Not so great. Not so great. Let's define our hash function a little bit differently, okay, so that we minimize this to some extent. Okay? Here's a better definition. Any algorithm that maps data to a number that is deterministic, that's what we had before, and that maps to a fixed number of locations. Now, that's actually what we had before too, but fixed being small, I guess you should probably say, or limited number of locations. We need to conserve space here. For that 700,000 word dictionary, maybe we only want to use 800,000, like a list that has 800,000, or an array that has 800,000 places in it, for extra words that maybe we add, right? But we have to store arbitrary words. So now we're kind of in trouble, OK? We want to be able to add any word and have it have its little place and fit in somewhere, OK? And we want it to be any length as well. Okay? So now we're running into a slightly different problem. Well, what we can do is we can do the same thing we've used before to minimize the size of your the size of an array and the size of something when you have numbers that actually go beyond it. All we need to do is the modulus operation or the percent operation. Okay? Sometimes hashes can be negative, as it turns out. And so mod is a little different than percent, because the percent is the modulus function, but only works on, well, it's not necessarily strictly defined for negative numbers the way you might think. But either way, take the modulus of the number. So if we have, let's say we have 10 buckets, right? And we get a number that is 26 out of our hash, right? Well, what we're going to do is we're going to mod it times 10 by 10, meaning that we will put it in bucket number 6. Okay? And now you've got 10 spots, and you can have any number, but as long as you do the modulus function on it, you will end up putting it into one of those n minus 1 spots. Okay? Well, n spots, 0 to n minus 1. Okay? In that case, what we say we have done is we have compressed that hash. Okay? We've compressed it down to the amount of space. Can anyone see the problem with this? What may happen eventually? I'll give you an example if you can't. Yeah, Kuyan.
So a bucket can have 2 values.
There we go. This is what you said before. A bucket can actually end up having 2 values in it. Okay? We call that a collision, and that's one of the problems that we have. Okay? But here's basically what we're looking at here, right? And we'll get to that collision in a second. N is the number of keys or words that we want to store. And big N in this case is the number of buckets that we're going to store them into. And we want N to be roughly the same size, maybe a little bit bigger. It actually helps if it's a little bit bigger. Well, it helps if it's much bigger, but as it turns out, it helps if it can be just a little bit bigger and still be fine. And but small, much smaller than the number of possible keys. And that's where the issue actually comes into play. Okay, we did this. Hash table maps to a large set of numbers, or a large set of buckets, or rather a small set of buckets, okay, with this compression function. Here's an example of that. And we kind of already went through this. Let's say you are going to do you have a table that you only want to be 10, just like what I said. Most of the time, by the way, we want these table sizes to actually be a prime number. As it turns out, you want it to be a prime number. Because prime numbers, when you take modulus, turns out that it orders them in different, it orders them relatively spread out in there. We'll get to examples of why that makes a difference in a little bit. But here's what we're going to do. We're going to have table size of 10. Here's our hash code. It's going to be a hash code on numbers, not letters right now. We'll go back to letters in a bit. And we are going to do the number modulus 10, and that's our whole hash function. Easy. It's easy to compute. It's easy to figure out. And what we want to do is insert the following numbers, 7, 18, 41, and 34. And again, all we do is just put them in based on their second character, or second digit in this case, their units digit, right? So 7 goes in the 7, 18 goes in 8, and 41 goes in 1, and 34 goes in 4. So far, so good. How do we find them? Easy. If you want to find where, and by the way, normally this would have some be like, normally this wouldn't be the key. Normally it would be the like whatever the value is associated with 34. I'm just going to put it in the numbers here to make it a little easier to understand. But if you wanted to find 34, well, you apply the hash and then look in that bucket. And there it is. Easy enough. And again, this is still order 1. But the problem is, of course, oh, can you do find max and find min on this? Yeah, that's not really possible in the sense of being a specific hash table. Why? Because there's no ordering at all, and there's no way to really, you could certainly do a linear search through all these and find it, right? But that's going to be a different operation, not one of our 3 big operations. But finding mins and finding max, not so good. Use a heap for that if you're going to do that. Okay? All right, if we try to add 54, well, there's our problem, right? Because 54 also goes into this same bucket here. And I've got a problem. This is called a collision. And it's kind of the biggest stumbling block in hash tables. Okay? There are lots of ways to deal with collisions. Today we're going to talk about one in particular. And in next week, we're going to talk about some other different ways of dealing with these collisions. Okay? But that's the problem. 2 hash tables. Anybody think they know a method for dealing with that? Off the top of your head, how might you go ahead and deal with that? Yes?
Well, I was thinking you could have, so the 0 time, instead of being like buckets of individual things, it could be buckets of dynamic arrays.
Ah, they could be buckets of dynamic arrays. Sure. And you would have 34 going to one and then 54 going to the other. Good point. Let's say that it was just definitions in here instead of the keys. How do we know which one relates to which one? You can't, right? It's not possible. You have to store the keys in that case with the actual thing. But yeah, that's a good way. Dynamic array is not a bad idea. What's another way we could do it? Yeah? Could you make a parallel array to that? You mean like 2 arrays? You just have another whole array? Interesting idea. I suppose you could. You'd have to link it together. I mean, you'd have to know which one to look in, which is kind of the issue. But that's not, I mean, that's an interesting idea. I don't think you'd necessarily want to, because if you build your hash function right, and I'm not saying this is right, because there's lots of different ideas for better hash functions than that. If you build it right, you should probably spread it out as much as possible so there won't be too many collisions. That's the idea. But yeah, OK, what is this? If this is a number, then a number, then a number, then a number, then a number, what does that actually look like? And what else? What other structure could it be? A linked list, right? You could have a linked list. These are each individual linked lists pointing to definitions with their associated keys. Good. All right, so that's what it is. We've got a hash table. Several keys are hashed to the same place. Oh, no. And that can happen if you limit the number of buckets. It's just going to happen. It's going to happen. Okay? And we already talked about this. How do you know if you've got the bucket that has multiple things in it? How do you know which one? You have to store the keys with the actual definition. So you go along and you find that linked list. And you say, oh, it's a linked list. Is this the key I'm looking for? Is this the key I'm looking for? Is this the key I'm looking for? Or you store the hash. I mean, either way. But or, I'm sorry, you can't just store the hash. You actually have to store the actual key itself if you're going to do that method. Which, by the way, is not necessarily the best way to do that, this linked list idea. If anybody lost their password for like a computer system around these places, right? When you email the tech support, do they email you your password back? No, they don't. Do they say, come on down, we'll tell you what your password was? Like they have it in some secret database? No, as it turns out, this hashing idea actually has cryptographic functionality in that hashes are only one way, right? You can only get to a hash, and you can't get back from a hash to the original key, at least if it's built right. Right? You won't be able to do that. So hashing is actually interesting in the sense that, like when you go to change your password, they have to change it to something new. They can't say, oh, here's your password. There's no way for them to tell what your password is, which is good for security, right? I mean, you don't know those guys in tech support. You don't want them knowing your password. Right now, they can still see all your files, but that's a different story altogether. But the point is, they don't. Let's say, you know, your password was the same, even though you shouldn't use the same passwords. Let's say you use the same password for different systems. They wouldn't be able to use that same password for some other system, okay? Because of the way it works. All right. So anyway, now we're going to store that. We could store the keys with the definitions. Maybe not the best idea, but we could do it that way to find it in a linked list. This is kind of a crazy drawing here, but here's all it is. It's just showing you that these are linked lists, right? We have our table here, which is a pointer to an array, right? And in this array, we've got a bunch of buckets. X's happen to be not filled. Okay, the empty spaces are the ones that have, or the ones that have arrows are the ones that are filled, right? And so for this one, let's say novel and supercalifragilisticexpialidocious both hash to the same value, 0 in this case, let's say, is the first one. Then the linked list would first point to novel. And if you wanted to look up the definition, you'd go, if you want to find novel, you'd go, OK, I hashed novel, it comes to 0. Is the first one novel? Yes, that's the definition, book, right? And if it's not, is it the next one, et cetera? Okay. Is this going to kind of degrade that whole order 1 thing? Yeah, it is, right? It is in the sense that if everything hashed to the first bucket, it would just be a linked list, right? That's why you want to build these good hash functions. Okay. Same thing here, same thing here. This one happens to point to hint. Did you know Shakespeare invented like a zillion different words? Like he invented tons of different words. Hint. Shakespeare invented that word, right? I think he invented the word excellent. I mean, like big words, like words we use all the time, like Shakespeare invented them. One of the reasons they make you study them, right? And then in these individual boxes, what you've got, you can have like you've got the actual linked list to the name, the key and the definition, and then maybe other definitions or something like that. No big deal in that. But you get the idea. You have linked lists on each array. Okay, questions on that one? Okay. All right. We have the operations. I've already talked about these. Insert, find, and remove. And this is how you actually implement them, right? To insert, you compute the hash code. You compress it. In other words, do the modulus function on it to compress it, or some other function that is well defined. And then you insert it in the right place, order 1. Find, hash the function, search the entry. If you find it, or if you have to look through a linked list, do the linked list search, return the entry. Also order 1 unless you have a linked list that's long. And remove key. Okay, same thing. Hash it, search the list for the given key, remove it if found, change the pointer to no. Pretty straightforward stuff as far as doing it. Okay. What if we tried to add the same key? Then you've got other issues, right? If you try to add the same key, right, well, at that point, then you've got a couple different ideas. Now, this is depending on what your use case is. You can do lots of different things. There's 2 basic approaches, right? One is, well, too bad to the old value, right? It's replaced with a new value. And that's actually the way Python dictionaries work. If you add an entry that happens to have the same key of some entry that's already in there, the other one just gets deleted. Okay? Or, what was the other approach? It's gone. The other approach is to make some decision about which one gets in there. You could have another list. You could have you could return both. Some functions say, OK, you can put as many as you want on the same key. We're just going to give you all of them back. It could give you a random one back. Depends on your situation. One thing you have to be careful about when you're talking about hashes, right, is you have to be careful that you don't change the object in some way that you used to make that hash, right? What's a good example? Let's say that you have an object and it's got a bunch of different properties in it or a bunch of different private variables. And you say, oh, what I'm going to do is I'm going to hash based on those variables, right? And I'm going to say that now I'm going to use that to make my hash. If you change any one of those variables, the hash will be completely destroyed and be a completely different hash. At least that's the idea, to make a completely different hash. And by the way, that's another good one for passwords. If you have a password, let's say you have a password that's like, Ben has a password that's happy, and Chris has a password that's happy with an I, because he thinks he's being sneaky and making it so that people won't guess, right? Well, the hashes for those 2 passwords, even though almost all the words are exactly the same, the hash for that should be completely different. So that even if someone does know Ben's password is happy, right, and he can't look at the hash and say, oh, Chris's password is pretty close to that hash. It's also got to be something like happy. So I'll try different versions of that, right? Hashing should be completely, and most hash functions actually do that as well. But you've got to be really careful that you don't change the hash code based on the, or you don't change the property that you based that hash code on. Otherwise, you won't ever find that hash again. Okay? All right. A couple other things on this. One of the, and we'll get into more details on this next time around. There's a load factor for a hash table. In other words, if you have so many keys that you're going to add, and you have the number of buckets that you're going to put them into, we can do a little ratio here and say that small n divided by big N gives us a load factor. In other words, how loaded up is our table? If the load factor stays low, right? If the hash function is good, and the compression function is good for various definitions of good, and there aren't any duplicate keys, you're going to get order 1 time. Okay? That's great. Okay? If there are no duplicate keys, which means that you can have a load factor that's not bad. I mean, you can have a load factor that's close to 1, and if you've got the same the good compression and no duplicate keys, you'll actually get this order 1 behavior, which is exactly what we're looking for. Okay? If the load factor gets too big, in other words, the number of items in here are going to be much bigger than the number of buckets you have, well, you're definitely going to have lots of collisions, and then you're going to start to degrade your performance. Okay? I say theta n time, big O n time is fine. That's not what you want to actually do. You don't want the load factor to get too big. In other words, if you start adding more and more and more of your elements and the array is only this big, make a bigger array. Come up with some other hash function or modulus function to do it. Okay? All right. So a couple things on hash functions that we've kind of already talked about. Hash codes themselves must be deterministic, and they should be fast and distributed. We really haven't talked about this distributed too much yet. Okay? What you want is in those buckets, you want to distribute the values through them. Here's what I'm going to do. Okay? I'm actually going to hash you guys. So it's going to mean getting up, and it's going to mean walking around the room, but that's good. Use the exercise, right? No, you're all in great shape. Here's what I want you to do. See the numbers around here? Okay? What I'm going to do is I'm going to give you a hash function. Okay? And it's going to be based on your birthday. Okay? The year and the date. Now, I don't care when your birthday is. Some people seem to have problems with like when their birthday is, right? Here's what I want you to do. Okay? First of all, your birthday, the year you were born, don't change the year. I mean, maybe a little if you want. If you want to change it by a couple, I don't care. But don't change it like by decades. Like don't say I was born in 1903, right? No. Keep it pretty similar, right? And then the other date, you can have whatever date you want. Just don't change it in this little exercise, okay? Leave it the same, okay? Here's the first one I'm going to give you. Okay? And what I want you to do is go as near as possible to the letter. You can't all like scrunch over next to 7 because it's in a row, right? But go as near as possible to the thing. Here's what I want you to do. I want you to go and hash yourselves based on the decade of your birth year. In other words, take the year you were born, divide it by 10, mod it by 10, and if you were born in the 80s, for instance, you would go to 8. If you were born in the 90s, you would go to 9. If you were et cetera, et cetera. Okay? Get up and go there. Well, I don't know. I don't know how old you guys are. Okay, so some of you guys are kind of slow. Bruce, are you participating? Okay, Bruce is participating. Bruce happens to be in 25. If I was participating, I shouldn't tell you guys. I would be in 7, believe it or not, right? And all you guys are like headed this way, right? Anybody in the 8s? Anybody see? Okay, there's one person in the 8s. Okay, it's other people. Most everybody else is in the 9s. Okay, question for you. Is this hash function, the decade of your birth, deterministic? Sure it is, right? I mean, all of you guys went there. If I sat you all down again and said, okay, go to your go to the decade of your birth year, you'd all go back to the same one, right? Is it fast? It is actually, well, you guys are slow. it's not that it's not fast. It was pretty fast. All you had to do is divide by 10, mod 10, you're done. That's your hash function. Not so bad. It's only it's pretty quick. Computer would do that instantly, right? Is it distributed? Ah, it's not. OK, that's a problem with this one. OK, the next one. Go to the last digit of your birth year. OK, in other words, if you were born in 1991, you're going to go to 1, etc. Okay. All right. Oh, look at this. It's in this case, it's things are changing a little bit here. Okay. All right. So I have no idea where all these people are going. Y'all going to 4? All 1994ers. Okay. So you're almost 20. Wow. Or over 20. All right. So okay, is this deterministic? Yeah, sure it is. Same thing, right? You know, your birthday's not changing. You're going to go to the right place every time. Is it fast? Yeah, sure. Same exact thing. In this case, you just mod it by 10. Easy. Is it distributed? It's better, right? It's certainly better. We've got more of a distributed. It looks kind of bimodal, right? 4s and 5s and 3s, or trimodal, or whatever. 4s and 5s and 3s, all there, right? Bruce, where'd you end up? And you ended up in the 3 category, right? So Bruce ended up in some other different hash, but with a lot of people, right? So that's, that's all right. OK, next one. Last digit of your birth month. OK, so if you were born if your last digit of your birth month was a 2, you go to the 2, etc. 12 or 2. OK, here's a 0. Oh, yeah, and yeah, zeros would be the 10s and the 10s, right? Ah. Nobody kill themselves jumping over tables, chairs, and things. All right. Hey, this one looks a little bit better, doesn't it? Is this one deterministic? Yes. Is it fast? Yes. Is it distributed? This one's much more better distributed, right, than the previous ones. Where are our non-distributed ones? Like, where's the kind of the bottleneck in this case? 2s and 1s, because people in both January and November end up in 1, and February and December end up in 2. Okay, so, but it is more or less distributed. You guys are all around. Last one I'm going to do. Was not up here. It's going to be the, what is it going to be? Any ideas? How about the last day of the last digit of the day you were born? It is on here. It's just not showing up. That's weird. All right. There we go. Ah. This one, is it deterministic? Is it fast? Is it distributed? Yeah, this one's way better, right? The only time you'd get an overlap here are the not pretty much completely distributed, assuming every birthdays are distributed. Which ones would overlap? Yeah, the ones, right? Because there's some, or there'd be more months with 31 days than 30 days. So you might end up with a couple extra people in that. Okay? But now you see how the hash function itself makes a difference. OK, grab a seat. This is a whole different problem, going back to your seats without having to climb over 12 people. All right. So, question? No questions. OK. So we kind of just saw, we hashed you guys, right, in your birthday. The ideal hash hashes to a random bucket. In other words, somewhere randomly across all number of buckets that you have. Okay? Is an ideal hash collision-free? Well, if it was collision-free, you would have to have buckets that allow for every possible key to hash its own bucket. So even the ideal hash is not going to be collision-free, right? Let's think about this for a second. Even the ideal, like even a great hash, right? If you had 2,500 keys and you had 1,000,000 buckets, what do you think the actual probability of having a collision is in that? 2,500 keys, 1,000,000 buckets. Pretty good for what? Pretty good for no collisions? Anybody want to guess a number, a percentage? 0.0%? Anybody else? 0%? Well, there could be a collision, right? 4%? OK. Anybody else? 20%? 20%? OK. So take a look at this. Let's see if I have it here. What I did was I wrote a little program called collision test. And what I did was I took 2,500 numbers and put them into a 1,000,000 character array using a very good hash function. OK? And the percentages you're going to see, and this is going to be doing it empirically. Like, in other words, it's going to keep running through this test. As it goes through there, notice what the percentages are for how often you have a collision when you have 2,500 keys going into a 1,000,000 character or a 1,000,000 element array. Okay? What? 97, 99, 91. So it turns out, how many people have studied the birthday problem in math class of some sort, right? There's 23 people in a room. 50%, there's a 50% possibility that 2 people will have the same birthday. This is pretty much the same idea. Okay, if you are randomly, and that's what I ended up doing, this function was randomly generated, like the hash was just to go to a random bucket, right? Because there are, even though there are 1,000,000 buckets, if you have 2,500 keys, the chance that one key or more actually collides is 95 to 97%. Okay? So even ideal hash functions do not have like a lack of collisions. Okay? And in fact, if you tried to have them a lack of collisions, you would degrade into some other type of structure, just by definition. Right? 2,500 keys are hashed in 1,000,000 buckets, 95% chance as on average. And you saw that kind of going along. If you average up all those numbers, I bet it'd be about 95%. Okay? So what are some good compression functions, or what are some good hash functions that we're going to use? Well, a bad compression function would be, let's say you had the keys are all integers, and the hash code was the integer itself. Right? Well, if the compression function was the hash code was the hash itself, and the compression function was the hash mod n, what if your compression function, well, in this case, 10,000 buckets, that one's not good. Let's say the keys are actually divisible by 4. Well, guess what? Your hash function is also divisible by 4, and therefore 3/4 of the buckets are not used. Right? So that would be bad, a bad hash function. If all of a sudden you had all this space, and you only ended up putting it into 1/4 of the positions. Bad hash function. In this case, what we're going to do is not mod n in this case, but mod by some prime number. This is where the prime numbers come back into play. Okay, why prime numbers? Because it ends up, if you take the modulus of a prime number, well, it's not divisible by anything, right? So therefore, it will randomly place it somewhere in the buckets. Okay, one good way to do it. Okay. Don't have to write all this down. It's online if you want. Here's a really good one. You don't have to know why this is a good one, except that there's some specific things about it. If you took the string and you if you took an integer, positive integer, multiplied it by the hash code that you came up with, add it to some other positive integer, take the modulus of some big, large prime number, and that's what the modulus is doing. It's scrambling them, right? And then mod it by the number of buckets. Then you get actually a very good hash number, a hash function. Okay, this is actually a pretty good one to use. If you ever want to use an easy hash function, go back to these notes, grab this one, use it, you'll be fine. Yeah, question.
Is there like any better value for A and B, or just like?
Right, there are better values for A and B. I think you can find them online, probably tables of fairly good values of those. Okay, and in this case, the number of buckets in this case doesn't need to be prime, which it could have been before, but we don't really like prime numbers as far as array lengths because it's harder to expand the arrays or whatever to, or it's hard to make them bigger because you always have to find a new prime number. In this case, if you use this hash function, no worries about a prime number. Okay. All right. So let's see. A good hash code for character strings. If their character strings go up from 0 to 127, which is kind of what we were doing yesterday in the try lab. Here's a pretty good one. Here's a giant prime number. Well, not actually. That's kind of all things considered, this relatively small prime number, but it's a prime number that's relatively big, right? And it's going to be 127, which is the number of characters you have, times the hash value, which you hash by, I think in this case I actually didn't do, and here it looks like 0, which is not what I wanted to do, but I don't know what I had there. And then you add it to the actual key value and do the modulus by p, and it works out OK. Okay, why is it good? Uses a large prime to mod and uses each character in the string. Okay, so you go through each character and you do it. Sometimes using each character is not always the best idea because if it's long words, you have to do it on every little character, and that's not necessarily the best way to do it. Okay. Bad hash codes. There's lots of bad hash codes. You can think of plenty, I'm sure. If you just added up the ASCII values and said, OK, here's my string. I'm adding up all the characters, and then that's my hash code. Not so good. Why? Normally not more than 500 for most words. That means only 500 buckets, right? Anagrams will always collide, right? Not the biggest deal in the world, and then the time to hash is proportional to string length, and you don't want to necessarily go through all the strings. What if we were to choose the first 3 letters in a word? Then you'd only need 26 to the 3 buckets. That's fine. Problem is, lots of words begin with the same prefix, right? And those words will all collide. If we changed our prime number to be 127, well, that would work, but then everything would end up being 0. Not good. So there's lots of different bad ones. You can look through this list a little bit later if you want, but lots of bad ones in this case. Okay? All right. So next week, we've kind of started hash codes. First things first, the lab's going to be on hashing. Okay, so you kind of play around with this idea a little bit. We're going to talk a little bit more about the load factor and how we can play around with the load factor to make better hash tables, as it turns out. We're going to talk a little more about hash tables itself. We're also going to talk about different strategies for collisions. That strategy where you have the linked list going in there is good, but it's not the best, especially since you have to keep the keys with them as well. There are other methods which are kind of neat as well, which don't require you to have any linked lists, believe it or not, or any lists at all. You actually find a different place in the table and go to that place that's empty, which you can generally do if you're less. Well, you can always do if you're less than the number of total keys that you're trying to store. We can also talk about perfect hash functions. If you happen to know all the keys ahead of time, right? Well, then you can come up with a perfect hash function. Why? Because you can assign it based on those keys and say, I don't need any more, and I know nobody will have any collisions. So we'll talk about that. We will also talk about, is there a case where a hash function should be slow? We talked about when it should be fast. There are some very important cases where hashing should be slow, which seems completely unintuitive, considering everything we've talked about has been faster, faster, faster. Sometimes we want things to be slow. Think about that while you're like thinking about this weekend, right? And we'll talk about where hashes are actually used, like in real-world programs, why we use them. Some programming languages, like I said, Python and I think Ruby, everything's a hash. Like they're like, oh, we've got this hash table. We're just going to remodel everything so it fits in this hash table and just deal with it, right? And it's because it's relatively straightforward. It gives you very good access times and search times and insert and remove times. And you can also, if you use some other tricks, you can mold it into most other data structures. So it can be all right. Questions on that? All right. Any other questions on the homeworks or anything? OK. I'll see you guys Monday.